beams that are expected to yield and to be damaged, but to protect the rest of the structure. The challenge with this philosophy is that it makes our buildings safe, but not resilient, or it makes them difficult to repair after an earthquake. For example, this is the PricewaterhouseCoopers building in New Zealand, where it was. The picture on the left is showing the building after the earthquake, so it doesn't look like it was damaged at all, but the beams within the building were damaged the way that the building was intended to perform. And so after the earthquake, even though the building did not collapse during the earthquake, they needed to tear the building down because there was damage in the building that was difficult to repair. And we will have the same problem in the United States if we have a severe earthquake. Our buildings, they're designed to be damaged and not necessarily repairable. One of the problems with that is if you have to tear down your buildings, it takes a long time to rebuild the city. And in Christchurch, they're still working on replacing the buildings that they had to tear down after the earthquake. Look to the side with some other plates that are welded to the. And then there's a plate that's welded on the front for the beam to attach to. The beam just has holes in the flanges and the web for assembly, and then the beam is attached to the column with these top plates and what I'm calling a fuse plate down at the bottom. The fuse plate has a unique geometry that allows it to be the weak link in the system so that it will yield rather than the beam. So to summarize, the connection, it's rigid during wind and moderate earthquakes, but during a severe earthquake, the fuse plate yields in shear, as I'm showing below, or to the right. Let me show you some pictures and video from experimental testing that was done to verify that this connection can indeed withstand large deformations during an earthquake and then be replaceable. So this video, I'll start it. When we test the connections in the laboratory, there's a standard protocol that we follow, and so we put small deformations on the connection and then work up to larger and larger deformations. So this is at 1% drift, meaning the building is leaning 1% of its height to the side. Once we get to the larger drifts, what this video is showing is that the fuse plate down at the bottom, it's yielding in these regions that are showing up as dark, and as you get to larger and larger deformations, that yielding increases until eventually we fatigue the plate. After the test, we could take the fuse plate off and put another fuse plate on and run the test again. And in my paper, that's what's described as two of these many tests that we've conducted. This is just summarizing the damage at different levels of deformation. So just for reference, in the United States, we typically design buildings so that they don't exceed 2 radians of drift. The connections need to go to at least 4 radians to qualify as a high seismic connection. And what we're showing here is that we can get to even much larger drifts before our plate is fatigued. So in the paper I described 2 tests, and we present results that look like this. So this plot is what we use to determine if our connection is good enough to qualify as a special moment frame. And so on the bottom axis we're showing the drift, and we need to get up to at least 0.04 radians of drift to qualify as a special moment frame. And on the vertical axis I'm showing the moment at the column face. That's the strength of the connection. And it needs to be above 0.8. That's the kind of the nominal strength of the beam. So what the plot is showing is that the tests satisfied those requirements and exceeded them. These two plots I'm showing are two tests that were run on the same beam and column. We just ran one test, B1, with a particular fuse plate, and then we changed the plate and run another test to show that the connection is still good and is repairable. Some of the benefits of this connection are there's no welding during construction out of the job site, and so that allows the steel building to be assembled very quickly because it's just bolted together. Another benefit of this connection is it allows us to reduce the amount of lateral bracing that's provided on the beam, and so that can save some weight and simplify the construction. So, in conclusion, our test showed that this connection is very successful in preventing damage to the beams and columns, which would be difficult to repair after an earthquake. The connection satisfied the requirements for special moment frames, and so they can be used just along with our existing codes. And the third conclusion is that the fuse plates, they can be replaced after an earthquake, so that rather than tearing down buildings with damaged beams, we can just replace plates to repair the buildings. So our company, Durafuse LLC, we have engineers that help people to incorporate this connection into their buildings. We help engineers size and optimize the beams and columns in their steel frames, and then we help with connection design, connection details, and schedules. And if any of you are interested in learning more, you can email this address.